Hello and welcome. Today we are doing the second dot point of Module 5. We are applying the modeling of projectile motion to derive the relationship between all of these variables. So for this problem, for this dot point, I'm going to set up a scenario. The scenario is this. We have an airplane. Bear with me while I draw some things. We have an airplane flying at 331 meters per second this way. 331 meters per second. There we go, beautiful. So it's flying 331 meters per second horizontally. That part's going to be important. And it drops a present along the way. So the present is not given any vertical velocity, but the present is going to have the horizontal velocity of the plane. Now, what we're going to do here, the question is to just derive all of these things. We want to work out every single one of these for the present. We need one more piece of information, and the piece of information I'm going to give you is the starting height of the present off the ground. That height is going to be 550 meters. 550 meters from the ground. Above the ground, I can draw better ground than that. Good. So this present is going to fall in a parabola. It's going to strike the ground some distance away from its starting position. It's going to strike the ground with some speed and at a certain angle. It's going to have a certain time of flight, etc., etc. So we're going to try and work out all of these things. Now, to solve these, it's going to be useful for us to first think about what it is we already know. So here we go. No, I'll write this in right here. Okay, so first of all, we want the initial velocity. The initial velocity is u. However, the initial velocity, as we discussed in the last video, we need to be able to split it up into its components. So we need to know what ux is. That's going to be the horizontal component of u, and also what uy is. Okay, so that is all for initial velocity. Launch angle. I'm going to put this in. No, I have to start a new one. Launch angle is going to be theta. Yeah, I'll turn that into a theta. Right, launch angle, maximum height, that's going to be displacement. And the height's going to be displacement in the y direction. Okay, so displacement y is going to be maximum height, displacement x is going to be the range. Now, up here it asks for maximum height, and it also asks for launch height. In this case, the launch height and the maximum height happen to be the same because it starts at maximum height here and only goes lower from there. For other problems, these could be different things. So I'm just going to write SY to stand for both of those. Okay, then we also have the all-important time of flight. Got to change my colors. Time equals something. We have the final velocity, same as initial velocity. We've got V for velocity, but we're also going to have Vx and Vy, right? We're going to be treating those differently to each other. And the horizontal range, that's going to be Sx. Okay, so we have all the variables we're trying to find. Now we just need to solve for them. What equations do we use? So if I pull up, oh, no, we're not solving for them. We're trying to work out what we already know. So u, initial velocity, it was given to us 331 meters per second. I'm trying to decide whether it's easier for me to try and write with my mouse or type. 331 meters per second. It's almost definitely better if I try and type this, isn't it? Let's put these in a nice color. 331 meters per second, horizontal. It is a vector, so it is important that we give a direction if we can. Ux is going to be 331 meters per second. We know it's horizontal because it's got x in there. And they're the same number because all of the velocity was horizontal, which means that uy is going to be 0 meters per second. When the present was dropped, It wasn't dropped with any vertical motion or it wasn't pushed down. It was just let go. And anything that's just let go is going to have a starting vertical velocity of 0. And that's going to be really important for trying to solve a lot of these problems. That number 0 is not given anywhere in the question, but you're going to have to know that it exists in order to work it out. This is not a 0, this is a theta. Let's make it look like a theta. And this theta is going to be 0 degrees from horizontal. And we know that, come on. And we know that because the initial velocity was purely horizontal. Okay. Sy, we don't know. Oh yes, we do know. Sy's displacement in the y direction, it's going to be 550 meters. It's actually negative 550 meters because the present started up high and its displacement was to go down 550 meters, and downwards is going to be our negative direction, upwards is going to be our positive. This actually leads us to another important variable, acceleration, which I'll put in here, acceleration, and that acceleration equals negative 9.8 meters per second, negative again because the acceleration is downwards. Okay, time we don't know, final velocity we don't know. Final velocity in the x direction, we actually know that that doesn't change. That's going to be 331 meters per second, same as it is up here. That is because this is a model of projectile motion. This model assumes there's no air resistance, and so that means there's no horizontal acceleration. Ux, Vx always stays the same. Okay, Vy we don't know. It's going to be going quite fast by the time it hits the ground in the vertical direction. And Sx, the displacement in the x direction, we don't know that either. So we're going to have to use some equations to solve for these four things. We can start in a few places. We could start with time, or we could start with final velocity. Either of those could possibly work. Let's have a look at the equations. So here's the formula sheet. You notice that no equations were given to us in the dot point itself. That's because these are equations that you are used to from the prelim course. Okay, these are the straight line motion equations, these first three, this one, and this one. And by separating the projectile motion into vertical and horizontal, we can actually use straight line equations. We can treat all the horizontal motion as if it was straight line motion, all the vertical motion as if it's straight line motion, and then use vector analysis to combine them at the end. Now with this information that we've got here, there are two ways we can approach this. We can use this top equation here. We know that, one thing about these equations is that they've all got acceleration. If you're looking at vertical motion, acceleration is going to be negative 9.8, and you have to make sure that every other value in here, which is a vector, is also the vertical version of that vector. So by S, it has to be SY, the vertical one. U has to be UY, vertical, because A is going to be negative 9.8, which I probably should write in here, is a vertical, let me try and draw it, is the vertical acceleration, AY equals negative 9.8, because AX is 0 meters per second, and A overall is going to be some beast which changes constantly over time, which we do not want to deal with if we can avoid it. So we can use this equation usefully. U is equal to 0 meters per second. So 0 times time is going to be 0. So it's going to be displacement equals, vertical displacement equals half of vertical acceleration times time squared. We can rearrange for time and work that out. I'm actually going to use this equation. I don't think there's any particular reason to use one or the other, but I'll just use this one here. I'm going to try and calculate V. Now, same as the one before, A here, I'm going to use negative 9.8. That's vertical. So my displacement is going to be vertical displacement, which I've got, negative 550 meters. My U is going to be initial vertical velocity, which is 0. A lot of people accidentally put in 331 there. And V, my final vertical velocity, Vy, is what I'm going to try and calculate It's the one that I do not know, which is good. There's one variable I don't know. We cannot use this equation v equals u plus at because we do not have time and we also don't have final velocity. So when there's two variables that you don't have, you can't rearrange it to find the answer to one of them by itself. So v squared equals u squared plus 2as is what we're going for. Let's go back here. I think we're going to have to bear with my handwriting with a mouse here. Let's try this. So v squared, oh, this is terrible, equals u squared plus 2, geez, 2as. Now we've got to remember that these are all in the vertical direction. So this is vy, uy, ay, and displacement in the y direction, sy. Okay, now rearranging this is not too hard. We're looking for vy, so we just have to get rid of this squared. So we square root both sides, not too hard. I was going to do this in full, but I might just cancel this squared out, put a square root over here. Hopefully you follow along with that fairly well. I can even delete this. Oops. Now that I've done that, I can even delete this squared over here to simplify everything. Okay, this is our formula. It's as easy now as plugging in the numbers. So Vy is equal to square root of uy squared, and uy is 0, 0 squared is 0, so we can just cut that whole bit out. Boom. Ignore that. Plus 2, so we need to keep the 2. I'm going to start putting in some brackets here just to simplify and just to aid in understanding. AY is going to be negative 9.8 and SY is going to be negative 550, what we've got over there. Negative 550. Okay, calculating this, we put in 2 times. We get negative 104 meters per second. So Vy, that is the velocity when it hits the ground in the vertical direction, is negative 104 meters per second. Now, when you put this into the calculator, you don't actually get a negative out. The square root actually gets rid of any possibility of a negative. But I know it's going to be a negative velocity because I know that when it hits the ground, it is going down. So I added the negative in. This is one example of where you have to use your knowledge of physics and the way the world is working in order to get the correct answer. So back to typing, Vy over here, negative 104 meters per second. Okay, one thing down. Let's do the next thing. Let's try and calculate time. So can delete all of this. So to calculate time, we now have vertical velocity. We can use that in here to calculate time. We've got final velocity, we've got initial velocity, we've got acceleration to work out time, or we can work out time the way I originally said. This one's going to involve a lot of rearranging, which I don't want to have to write out by hand here. So I'm going to use the simpler equation, v equals u plus at. And I'm going to write it out by hand. V equals u plus at. And I'm doing this multiple times so that you remember that they all have to be in the same direction. We are using the y direction for this equation. So Vy equals uy plus ayt. T doesn't need a y because t is not a vector. Okay, we need to rearrange this for time. That is what we're working out. I'm going to do it all in one go to save myself from having to write extra things. So uy, we're going to minus uy to both sides. So it's going to end up over there as a negative. Then when it's vy minus uy equals ayt, we're going to divide both sides by ay. So we're going to divide both sides by ay to get t by itself. So we end up with t equals vy minus uy over ay. and that's simply putting in the numbers. Yeah, I'll write them up. Vy is negative 104, 104. Uy is 0, so 104 minus 0 is just negative 104, divided by Ay, which is negative 9.8. You can see if we're not consistent with our negatives here, we'd end up with a negative time, which would not be correct. So our time, if we calculate that, is 104 minus 9.8 is 10.6 seconds. 10.6 seconds. Always putting units into these things. Time over here, 10.6 seconds. Okay, we are making some progress. Can delete all of that now. Next thing, we have two more things we can calculate. We have the range. Over here it says horizontal range of the projectile. That is displacement in the x direction. And we also have final velocity. We can go for either of them now. So let's go for range first. To work out the horizontal velocity, to work out the horizontal displacement, we actually just need to use this number here, 331 meters per second, and time 10.6. A lot of you will know it's not in the formula sheet, but you know that speed is distance over time. We're going to be using that. It actually kind of sneakily is in the formula sheet because acceleration is 0. If you put a 0 in here, half times 0 times time squared is nothing, and we end up with displacement equals velocity times time. And that's really what we're using here. So I'm going to be copying this part of the equation over. I'm crossing all of that out because our acceleration is 0. So S equals ut, writing that in here. Displacement equals velocity times time. And this is only working because we're now using horizontal. So this is Sx, displacement in the x direction or the range, equals ux times time. Simply, ux we've got is 331. 331 times time, which we worked out was 10.6, equals Sx. And if we calculate that here, that gives us a large number, 3,509 meters. 3,509 meters. Good for Sx here, 3,509 meters. That's the horizontal range. The only thing left to do, and sadly the hardest thing to do, is going to be getting this final velocity. The hardest thing really is picking the right equation for the situation. But when I say hardest for me, it's going to be writing by hand everything in this space. So to get the final velocity, it's not actually that difficult. We need to use vector analysis. The projectile at this point here is going to have some downwards velocity, it's going to have some horizontal velocity, and we need to combine the two to get the final velocity. So the downwards velocity, the horizontal velocity is going to be a vector with value 331 meters per second. And the downwards final velocity, we worked out down here, it's Vy, it's negative 104. Negative means I draw my vector downwards because I chose that as my negative direction. And the value is 104. So the downwards arrow is the negative, 104 meters is the magnitude. That just means that my final velocity is going to be a vector which is equal to the addition of the horizontal and vertical components. To work this out, I can use Pythagoras theorem, a squared equals b squared, a squared plus b squared equals c squared, or in this case, that's going to be, this is velocity in the x direction equals, and this is velocity in the y direction. So it's going to be velocity squared equals velocity x squared time plus velocity y squared. So we can, so we can say final velocity is going to be equal to the square root. taking some shortcuts. It is started off as v squared. I'm cancelling out that squared to put this square root in here. V squared, v equals square root of vx squared plus vy squared. So I just substitute some numbers in. I'm just putting 331 into here where it says vx. I'm putting 104 down here where it says vy. And I end up with 347. So over here, this red arrow here, I'll draw it in red so you know, is going to be a value of 347 meters per second. That is the final velocity. 347 meters per second. And that makes sense. You know that the hypotenuse of a right angled triangle is going to be the largest number, and 347 is larger than 331 or 104. However, it is a vector. If this question was asking you to find the final velocity, you would have to find this number, but you'd also have to find the angle at which this vector is. So if we were to try and find the angle of this angle theta, which is going to be the angle from the horizontal, we can use some trigonometry. Let me delete some more stuff. Let's get rid of this. So to use trigonometry for this part, we can use SOHCAHTOA. We can use any part of SOHCAHTOA because we've got all three sides. So let's just use sine. That's going to be sine theta is equal to opposite over hypotenuse. In this case, opposite is going to be the side opposite to theta, which is 104, which is going to be Vy. The hypotenuse is V, 347. So rearranging theta equals sine to the -1, or inverse sine, opposite, 331. Sorry, that's not correct. Opposite is this blue arrow here, 104, divided by the hypotenuse, which is 347, which gives us a value of 17 degrees. So theta equals 17 degrees. So in the end, 17 degrees, when we're writing down what the final velocity is, get rid of all of this, we have written 347 meters per second. We have to add to that at 17 degrees below horizontal. I'm going to draw the degrees in here. There we go. Because it is a vector, this would be your final answer. One last thing. Here I've just sort of rounded up most of my numbers to 0 or 1 decimal place, but you would have to do the right number of significant figures for the exam. In this question, you are using this value, -9.8, which is 2 significant figures, so you'd want your answers to also have 2 significant figures. The other 2 values given in the question, 331 and 550, both have 3 significant figures. You always have to choose the one with the least, which is 9.8. So to write this to 2 significant figures is 350 meters per second at 17 degrees below horizontal. And that's finally it. Hopefully this didn't take too long, 24 minutes. Oh my gosh. Yeah, we might even do a more complicated problem next time if I can deal with it. Bye everyone.